Hello. In this section, we are going to introduce the concept of the confidence interval. Specifically, today's topic is how to find a confidence interval to estimate a population mean with the condition that sigma, which is the population standard deviation, is a known value. Now, today's topic, this is one of two kind of large remaining topics that we're going to cover in this class. After we're finished going over confidence intervals, we will, the last topic that we'll cover in the class is hypothesis testing. Both of these last two remaining topics will rely heavily on the sampling distribution. They're they're good examples of how the sampling distribution can be used in some really unique and helpful applications. So let's go ahead and dive right in here. Okay. So the purpose of a confidence interval is it's a way of creating an interval that's used to estimate the value of a population parameter. And in this section, we will be focusing on the population mean as the parameter that we are trying to estimate. We'll introduce this concept which we called critical values. We'll define that term a little bit later. We'll look at the relationship between the confidence level and the margin of error. And we'll kind of wrap up by going over sample sizes, how to find the sample size necessary to obtain a confidence interval of a given width. So first of all, let's just go over the basics here. So let's start off by just looking at this example. Let's say that a simple random sample of 100 fourth graders is selected to take part in a new experimental approach to teach reading. At the end of the program, the students are given a standardized reading test. On the basis of past results, it is known that scores on this test have a population standard deviation of sigma equals 15. Now let's say that we, all 100 students, right, they're given this test, and then after they take the standardized reading test, their scores are all averaged, and we find out that the mean score for the 100 students was 67.3. Now really the administrators would like to estimate what the mean score would be if the entire population of fourth graders in the district had enrolled in the program, right? The 67.3 value is the average score for only the 100 students in the sample, not for the entire population. So the best estimate that we currently have for the population mean is the sample mean of 67.3. It's pretty unlikely that that sample mean is exactly equal to the population mean, right? The population mean is the value we would like to know. The sample mean is the value that we are able to calculate, right? Because we only have access to this sample of 100 students. So in this case, we refer to the sample mean as a point estimate. A point estimate is a single number that is used to estimate a population parameter. Okay, so a sample mean is a point estimate for a population mean because it's a single number. Now, it's very unlikely, like we said, that 67.3 is exactly equal to the population mean, which is denoted by mu, of all fourth graders. So in order for the estimate to be useful, we have to somehow describe how close it's likely to be to the population mean, right? For example, maybe we think that the sample mean could be off by as much as 10 points. In that case, we would estimate the population mean with the interval 57.3 up to 77.3, right? 57.3 is 10 points below the sample mean. 77.3 is 10 points above the sample mean, right? Another way we could write that is 67.3, and then we use the symbol plus minus, a plus and then a minus directly underneath, 10, right? So that would be 67.3, and then the interval would be anywhere from 10 points below that to 10 points above that. the plus or minus number is called the margin of error of our interval, right? So when we're developing a confidence interval, we have to have a method for determining the margin of error, right? We know how to get the sample mean. We just collect a sample, and then we calculate the mean based off of that. But how do we determine this margin of error to develop an interval for estimating the value of the population mean? That's what we will explore in this section. So actually, to find the margin of error, we will use the sampling distribution. And what we do is we will define this term level of confidence, right? So the level of confidence is a measure of how confident we are that our interval is one that the interval we construct is one that actually contains the value of the population mean, right? And confidence levels can be chosen to be anything we want them to be, but because we want to be very confident that our interval does contain the population mean, we typically choose a level of confidence that's pretty high, right? Something like 95% is a common choice. Suppose we want to be 95% confident in our interval. So what we need to do is we need to determine how large to make the margin of error so that the interval is likely to contain the population mean. And we'll do that by using the sampling distribution. Now recall, according to the central limit theorem, that if we have a sample size that is greater than 30, the central limit theorem tells us that the sampling distribution of the sample mean is approximately normal, and the mean of the sampling distribution is equal to the population mean. The standard error, or standard deviation of the sampling distribution, is defined as the population standard deviation over the square root of the sample size. So we went over all of this in Chapter 7, specifically Section 7.3. So now I want to kind of walk you through a process here that we can use to kind of derive a formula for for finding a confidence interval to estimate a population mean. So let me get my pen up here. Okay, so let's start, and this is where I like to start. Let's start with just the standard normal curve, right? The standard normal curve is the normal curve of z-values, okay? And remember, it's going to be centered over 0. And what we want to do is we want to develop a formula for a 95% confidence interval. So what I'm going to do is I'm going to say, okay, there are two values. I don't yet know what those values are. They're z-scores, z-values, right? And the area in the middle between these two values is 0.95, okay? 0.95 because we want a 95% confidence interval. So this is my starting place. Now, the blocked out area, that's an area of 0.95, is right in the middle, right? So what I'm going to start with is I'm going to use the standard normal curve chart to figure out what are the z-scores that bound this. Now, keep in mind that the total area under the curve is equal to 1, which means this area here and this area here, they have to add up to equal 0.05, right? Because the total area under the curve is equal to 1. And then furthermore, because the curve is symmetric and the 0.95 area is right in the middle, this area in this tail and this area in this tail will be exactly the same size, which means that would be 0.05 divided by 2, or 0.025, okay? 0.025, okay? 0.025 plus 0.95 plus 0.025, they all add up to equal 1, the total area under the curve, right? So to figure out what the z-score is that corresponds to this boundary area here, I'm going to go to the standard normal curve chart. I'm going to look through the main body of the chart to find the area 0.025, because that's the area to the left of whatever that z-score is. And then I'm going to look up the corresponding z-score to that area. So let's just do that right now. Let's see here. Sorry. Oops. Okay, sorry. Okay, so here's my chart. So I'm going to kind of scan through here, and I see right here 0.025, right? And this is just, you pretty much have to just kind of scan through until you find it. 0.025. And sometimes with these sort of procedures, you might not necessarily find the exact area, so just find the area that's closest. But in this case, 0.025 exactly does show up on there, and that corresponds to a z-value of negative 1.96, right? And the negative 1.9 is over here, the 0.06 is up there. Combine those together to get negative 1.96. Let me go back over here to my PowerPoint. So that tells me that the area, I've got to get my pen back. And let me just make sure that it always defaults to red. I'm not sure why, but okay. So so this is negative 1.96. Now it turns out that because the curve is perfectly symmetric, and the 0.95 area is right in the middle, then the z-scores that bound that middle area are they're going to differ only by the sign. So if this is negative 1.96, this is positive 1.96. Okay, and so the number 1.96, we would call that the critical value that corresponds to a 95% confidence interval. Now, I'm going to make a statement here, a true statement based off of this. Let's say that we randomly select a z-score based from the population of all z-scores, right? We could make this statement. The probability that the randomly chosen z-score falls between negative 1.96 and positive 1.96 is equal to 0.95, right? And that's simply because when we first defined the normal curve, we said that a specific area under the normal curve can be interpreted as the probability that a value falls between those two endpoints, right? So because the standard normal curve is the distribution curve of all z-scores, right, then this statement is a true statement. Now, what's inside the parentheses there, that is going to be my starting point for developing a formula for the confidence interval. Now, for the confidence interval, I don't want to have a z, so I do have something that has a lower endpoint and an upper endpoint, right? But I don't want to have a z in there. I want to have the population mean value mu. But fortunately, we have a nice relationship between z and mu, and that is the z-score formula, specifically the z-score formula from the sampling distribution, which we looked at in section 7.3. That formula was x bar minus mu divided by sigma over the square root of n. Okay, this formula relates the sample mean and the population mean together, which is exactly what we want, right? Because the sample mean is something that we can compute from the sample data, and we want to be able to use a computed sample mean to then develop an interval to estimate the population mean. So I'm going to just take what's inside the parentheses here. I'm going to come over here, and I'm going to replace the z with x bar minus mu over sigma over the square root of n. So that gives me negative 1.96 is less than x bar minus mu over sigma over the square root of n is less than positive 1.96. Okay. Now I'm going to do a little bit of algebra, and my goal is to just get the mu all by itself in the middle and everything else on the endpoints. So I'll start by just multiplying the left, the middle, and the right by sigma over the square root of n. And that gives me negative 1.96 times sigma over the square root of n is less than x bar minus mu, which is less than positive 1.96 sigma over the square root of n. Okay? And then to wrap up, I have to basically I have to subtract x bar from both sides. From the left, the middle, and the right. But that's going to leave me with a negative mu in the middle. So then I would multiply the left, middle, and right by negative 1. And when you do all that, what you're going to end up with is this. X bar minus 1.96 sigma over the square root of n is less than mu, which is less than x bar plus 1.96 sigma over the square root of n. Okay? And what we have here is a formula now for estimating a confidence interval or for computing a confidence interval to estimate the value of the population mean. And notice how it's structured. We have the sample mean, and we subtract and add a value to the sample mean, and that value is the margin of error, right? The margin of error is found by taking this 1.96 value and multiplying it by sigma over the square root of n, right? So this, we said that was the critical value. Sorry, my handwriting is not great. And over here, sigma over the square root of n, that's the standard error. Okay. So the way you find the margin of error is you always take the critical value and multiply it by the standard error. Okay. And the critical value is going to be different depending on what your desired level of confidence is, right? This is the critical value that is based off of 95% confidence, right? But if you show something like 90% confidence, then the middle area would be 0.9 and the critical values would be different, right? But this diagram kind of illustrates how that critical value is defined. But the margin of error is always the critical value times the standard error. And then that margin of error gets subtracted and added to the sample mean. Okay? So this is the method or the pattern that we'll always follow for finding a confidence interval. Start with the sample statistic, which in this case is the sample mean, add and subtract the margin of error, and the margin of error is the product of the critical value and the standard error. Okay, let's go back to our example where we looked at the teach reading example. The standard error is defined as sigma over the square root of n. Sigma is given in the problem as 15. N is the sample size, which is 100. So it's 15 over the square root of 100, which equals 1.5. So we want to construct a 95% confidence interval for mu, right? So there's our standard normal curve, and the critical value is 1.96. When we worked through how to find that value just a minute ago, right? To obtain the margin of error, we multiply the critical value by the standard error. So that's going to be 1.96 times 1.5 equals 2.94. And then to find the confidence interval, we take the margin of error and we subtract and then add it to the sample mean, right? So that will be 67.3 plus or minus 2.94. And so the confidence interval says that we estimate that mu, the population mean, falls between 64.36 and 70.24. Or the specific language we would use is we would say, we are 95% confident that the population mean falls within that range. Okay, so let's talk a little bit more about this concept of confidence level. Okay. Right, so what we did in the example, based off of on the sample of 100 fourth graders using the new approach to teach reading, we constructed a 95% confidence interval for the mean score, right? So the best way to define confidence level is to think of it as a success rate of the method used to construct the confidence interval. This diagram illustrates this idea of success rate. If we were to draw many samples, right, each sample would have its own individual sample mean. When we looked at the sampling distribution, we talked about how the sample mean is a random variable, right? So from sample to sample to sample, the sample means will not all be the same. For each sample, we could construct a 95% confidence interval, right? And because we're starting with different sample means, then the different confidence intervals will have different endpoints, right? They will not all look identical. But our hope is that they would all, most of them would overlap somewhere within the value of mu, right? So this diagram, the vertical line represents the population mean mu. All the horizontal lines represent lots of different confidence intervals. And you'll notice that most of them overlap, right? Overlap the population mean, but a few of them miss, like this one misses, this one misses, this one misses, right? There's a few that miss. Most of them overlap. Some of them overlap close to the middle. Some overlap close to an end. But if you use a 95% confidence interval, if we use that as our confidence level, then we would say that the success rate is 95%, or we would say that 95% of the intervals constructed would overlap somewhere with the population mean. Okay, so that's the best way to interpret that concept. Let's go over some other terminology here, right? A point estimate is simply defined as a single number that is used to estimate the value of an unknown parameter. So a sample mean would be a point estimate for a population mean. A sample proportion would be a point estimate for a population proportion, and so on, right? A confidence interval is an interval that is used to estimate the value of a parameter. The confidence level is a percentage between 0% and 100% that measures the success rate of the method used to construct the confidence interval. And then the margin of error is computed by multiplying the critical value by the standard error. And then that margin of error gets added and subtracted to the sample statistic to get the lower and upper boundaries of your confidence interval. Okay, so we've kind of already touched on this a bit, but let's go over again, talk a bit more about critical values, right? 95% is probably the most commonly used confidence level, but it's not the only one that's used. We can really construct a confidence interval with any confidence level between 0% and 100%, but we pretty much always use percentages that are much higher, right? Because we want to be pretty highly confident in our result. When I kind of went through the derivation process, I walked us through how we could use table A3, which is the standard normal curve table, right, to find critical values. Now that works, that always works. It can be a little tedious to always rely on that method. So the table here just kind of gives us the critical values for several common confidence levels. So for most of the time, you can just pull your critical value off of this smaller chart without going through the whole process that I showed you with the big chart, right? So like for 95% confidence, the critical value is 1.96, right? That's what we walked through on the big chart, is how we would find that on the big chart. But this also shows it the same value here, right? If you want a 90% confidence interval, you would use a critical value of 1.645. If you want a 98% confidence level, you would use a critical value of 2.326, right? And then in each case, you would take that critical value, multiply it by the standard error to get your margin of error. Okay, so a large sample, and again, we define large sample as greater than 30, has a sample mean of 7.1 and a standard error of 2.3. Construct a 90% confidence interval for the population mean. So 90%, we would go to the small chart and we would see the critical value for 90% is 1.645. So we take that critical value, we multiply it by the standard error to get a margin of error of 3.8. So a 90% confidence interval would be found by taking the sample mean of 7.1, subtracting and adding the margin of error of 3.8, and we would end up with our confidence interval that mu falls somewhere between 3.3 and 10.9 with 90% confidence. Okay, so let's just take a look at this notation, which is used in our textbook, and not all textbooks use it, but it is a fairly common notation, so it's good to understand it. As we showed you, sometimes we may need to find a critical value for a confidence level that's not shown in the small chart. So then you can use the big chart to find it. But the Z-alpha notation, the Z subscript alpha refers to the Z-score with an area of alpha to its right. So the important thing here is that the subscript represents the area to the right if the Z-score is positive. So the notation Z subscript alpha over 2 refers to the Z-score with an area of alpha over 2 to its right. And then the opposite of that is that if the Z-score is negative, then the subscript represents the area to the left, right? So you can see in the picture down here, Z alpha over 2, the area to the right is alpha over 2. Negative Z alpha over 2, the area to the left is alpha over 2, okay? So typically the confidence level, which is the area in the middle, is defined as 1 minus alpha, which means that each of the tail areas, they're of equal size. Each one has an area of alpha over 2, right? Because alpha over 2 plus alpha over 2 plus 1 minus alpha, all that adds up to equal 1, okay? So then the critical value is Z alpha over 2, because the area under the standard normal curve between negative Z alpha over 2 and positive Z alpha over 2 is 1 minus alpha, which is defined as the critical value, right? And those Z-scores can be found. If they don't show up on the small chart, you can use the big standard normal curve chart to find those areas. Or you can use also the inverse norm command on your TI-84 calculator, which we talked about in Chapter 7. So for example, if you want to find the critical value Z alpha over 2 for a 92% confidence interval, 92% does not show up on the little chart, so we'd have to go back to the big chart to figure it out. But the middle area is 0.92, right? Which means each of the tail areas is of size 0.04. Again, because they have to be the same size, and all three areas, the left tail plus the middle plus the right tail, they have to add up to equal 1, right? So the critical value is Z subscript 0.04 because the area to the right of the critical value here is 0.04. And then the area to the left of the negative Z value is also 0.04, right? So really the area to the left of positive of z point of this number here is 0.96, right? The total area to the left, because it's 0.92 for the middle area, plus 0.04 for the tail area, right? 0.96. So if you want to figure out what this value is from the big chart, you would come over to the big chart and you would scan through the main body looking for the area that is closest to 0.96. In this case, 0.96 exactly does not show up on there, but 0.9599 does, and that's very, very close. And that has a z-score of 1.75, right? So your critical value would be 1.75 because it's the z-score that corresponds to the left area, 0.96. Or the alternate way to do that would be to use the inverse norm on your calculator. You would put in 0.96 for the area to the left, 0 for the mean, and 1 for the standard deviation because we're dealing with the standard normal curve. And that also, rounded to 2 decimal places, gives you 1.75 as your critical value. Okay. Okay, so that kind of goes over the basics, but let's just talk about some assumptions that need to be made in order for this method to work. One of the big assumptions is the assumption that sigma is a known value. And we have to make this assumption because the formula relies on the standard error, which is the sigma over the square root of n value, right? This is kind of a problematic assumption because in practice, sigma is usually not known. Sigma is a population parameter, right? It's the population standard deviation, and the only way to compute sigma would be if we had access to the entire population. If we had access to the entire population, we could actually just straight up compute the population mean. We wouldn't have to estimate it with an interval, right? So it's unlikely that sigma would be known. Now, in the next section, we will tweak the formula that we just derived and show you how we can still compute confidence intervals if sigma is not known. But it requires the basic format of the formula remains the same. It's still going to be critical value times standard error, but we have to make a few key modifications so that it still works if sigma is not known. So that will be the topic for the next section. But the other assumptions that we have to make are really the same assumptions that apply to the central limit theorem. The sample has to be a simple random sample, and the sample size needs to be either large, which we define as greater than 30, or the population is approximately normal. All right, so let's take a look at another example. A machine that fills cereal boxes is supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. It is known from past experience that the fill weights are normally distributed with a standard deviation of 0.2 ounces. So we want to construct a 90% confidence interval for the mean fill weight. So let's first check our assumptions. It does specifically say that it's a simple random sample. Now, so that assumption is met. The sample size is small. It's only a sample size of 6, but it also says that fill weights are known to be normally distributed, so the population is approximately normal. So the second assumption is also satisfied. So those assumptions are met. So the next step is to work on finding the margin of error. Now, the point estimate is the sample mean, which is given as 20.25. And we are asked to construct a 90% confidence interval. So we have to find the critical value corresponding to 90%. To do that, we go, the easiest way would be to go to that small table. Since 90% is one of the values that shows up on there, And we can just see that the critical value for 90% is 1.645. So then the standard error is sigma over the square root of n. Sigma is the population standard deviation, which is given as 0.2. N is the sample size, which is 6. So 0.2 over the square root of 6 equals 0.08165. So the margin of error then is the critical value times the standard error, which results in 0.1343. So 90% confidence interval would be the sample mean plus or minus the margin of error, which results in mu falling somewhere between 20.12 and 20.38 with 90% confidence. So there's a typical example of how to find a confidence interval. Let's go over how to use your TI-84 to find a confidence interval. It has a built-in function, which makes it pretty easy to do this. The function that you would want to use for what we've covered in this section is the function called z-interval. And it's in the tests menu, which you would access by pressing the stat button on your calculator and then highlighting the word tests at the top of your screen. Scroll down until you see and the seventh one down is the one that's referred to as z-interval. And for input, there are going to be two options for input, either data or stats. Data is what you would use if you're just starting with the raw data. Stats is what you would use if things like sigma and the sample mean and the sample size are already given for you. Okay? In the example we just looked at, we would use stats as the input option because the sample mean is already computed for us and sigma is given to us. In the next section, we'll look at an example where we use the data input option. But today, we'll just look at the stats input option. Okay, so you highlight the word stats. You'll get a screen that looks like this. For sigma, you'll type for this example, we would type in 0.2. For the sample mean, 20.25. N is the sample size, you type in 6. C level is the confidence level. If we want 90%, we would type in 0.9, highlight the word calculate, and press enter. So, and once you do that, you'll get a readout that looks like this. The confidence interval are the two numbers in the parentheses separated by a comma, the lower and upper endpoint of your interval. Then it also just gives you the sample mean and sample size right there as well. So that's, once you get familiar with that function, that can also be a pretty nice way to find a confidence interval. Okay, so let's revisit the idea of confidence level, right? So we said that the confidence level can be set to whatever we want it to. So it kind of begs the question, why would we choose a lower confidence over a higher confidence, right? We want to be confident that our interval contains the population mean. So why would we choose 90% when we could choose 99%, for example, right? Well, the reason is because there's always a trade-off. Yes, we would rather have a higher level of confidence than a lower level, but if we choose a higher confidence, that will also result in a larger margin of error, right? And having a smaller margin of error is also desirable, right? So there's kind of this negative correlation. If you increase your confidence, that's a positive thing. That also results in an increased margin of error, which is a negative thing, right? So that's why sometimes a slightly smaller confidence is chosen, like 90 or 95%, which is still high, so that the margin of error is relatively manageable as well. Here are 3 diagrams that illustrate this concept, right? 70% confidence level. The vertical line represents the population mean. The horizontal lines all represent confidence intervals. And the horizontal lines are pretty short, which means the margin of error is pretty small, which is a good thing. But you'll notice that a lot of them miss, a lot of them don't overlap with the population mean. That's a bad thing, right? So there's kind of like a 30% failure rate, which is not so great. The other extreme would be to choose something like 99.7% confidence, which means that we're almost guaranteed to succeed in overlapping with the population mean, but our intervals are also very wide margin of error, right? So that's not so great either. So oftentimes 95% is chosen as a good compromise between reliability and margin of error, where your margin of error is still fairly reasonable, and your success rate is also still quite high. So that's those are the factors that kind of go into that. Now, the one thing you can do to decrease the margin of error for a fixed confidence level is increase your sample size. But there's always limits to how high you can make your sample size as well, right? So you got to keep that in mind. That being said, usually when we are starting from scratch, what we do is we kind of decide, before we even construct the interval, we decide what is the maximum margin of error I'm willing to accept, and what is my desired level of confidence. Those are two things that are chosen at the very beginning. And then we figure out how big does the sample size need to be in order for those parameters to be met. And so we can actually come up with a formula to find a sample size to meet those requirements, right? It's pretty simple to do that. If we let m represent the margin of error, then m is defined as the critical value times the standard error, right? The z alpha over 2 is the critical value. The standard error is sigma over the square root of n. And just doing a little bit of simple algebra, we can solve that for n, which is the sample size. So n becomes the product of the z critical value times sigma divided by m, the whole thing squared. That represents the minimum sample size needed to achieve the desired margin of error, m. And oftentimes you'll find that the value of n given by the formula does not come out to be a whole number, but rather a decimal value. So that sample size always needs to be a whole number. So the best thing to do is to always round it up to the nearest whole number, keeping in mind that a larger sample size is always an improvement, right? Because that just reduces the margin of error more, right? So rounding it up is always a good thing to do, which won't necessarily be to the nearest whole number, but rounding up, we can guarantee that the margin of error is no greater than the desired value of m. So let's kind of wrap up with an example where we find a desired sample size. Scientists want to estimate the mean weight of mice after they have been fed a special diet. From previous studies, it is known that the weight is normally distributed with a standard deviation of 3 grams. How many mice must be weighed so that a 95% confidence interval will have a margin of error of 0.5 grams? Using our formula, we would use 1.9, right? The sample size is equal to the critical value times sigma divided by the margin of error, whole thing squared, right? So if we want a 95% confidence interval, as we've seen previously, the critical value for that is 1.96. Sigma is given as 3. M, the margin of error, is given as 0.5. Plug all those values in. Use your calculator, you would get about 138.3, and so we would choose to round that up to 139. So we would conclude by saying we must weigh 139 mice in order to obtain a 95% confidence interval with a margin of error of 0.5 grams. So that wraps up this section, right? We've gone over how to construct and interpret confidence intervals for a population mean when the population standard deviation is known We've gone over how to find critical values for confidence intervals. We've discussed the relationship between the confidence level and the margin of error. And we've gone over how to find the sample size necessary to obtain a confidence interval of a given width. And in the next section, we will continue talking about the confidence interval to estimate a mean, but we'll look at how do we do that if sigma is an unknown value, if we don't know the population standard deviation. So thank you for watching.